Hello everyone, and welcome to Robotics Today. My name is Luca Carlone, and I'm excited to introduce Naira Hovakimyan as our speaker today. Naira is going to talk about a very hot topic, which is self-learning and control. After her talk, we are also going to have a panel discussion, and today we are very excited to have two wonderful guest panelists, Claire Tomlin from UC Berkeley and Jonathan Howe from MIT. Naira is currently a professor of mechanical science and engineering at the University of Illinois at Urbana-Champaign. She got her Ph.D. in physics and mathematics from the Institute of Applied Mathematics of the Russian Academy of Sciences in Moscow. And before joining the faculty at UIUC in 2008, she spent some time as a research scientist at Stuttgart University in Germany. She was at INRI in France and at Georgia Tech. And she was also on the faculty at Virginia Tech. So in 2015, she was also named inaugural director of the Intelligent Robotics Lab at UIUC. Naira has been a pioneer in adaptive control. She's been providing a number of fundamental contributions to control optimization, autonomous system, neural networks, game theory, and she also did extraordinary contribution to applications in aerospace, robotics, agriculture, biomedical engineering, elderly care, among many other fields. She has co-authored 2 books, 6 patents, and more than 400 publications. Naira has received multiple awards. I will try to sample a few of them just to give you the flavor here. In 2015, she got the AIAA Mechanics and Control of Flight Award. In 2014, she was awarded the Humboldt Prize for her lifetime achievements. In 2015, she got the IEEE Control Systems Society Award for technical excellence in aerospace controls. In 2019, she got the AIAA Pendray Aerospace Literature Award. She's fellow and life member of AIAA and fellow of IEEE. And her work in robotics for elderly care was featured in the New York Times and Fox TV and CNBC. Besides being an excellent researcher, Naira is also an excellent mentor. In 2015, she was awarded the UIUC Engineering Council Award for excellent advising. And she's also co-founder and chief scientist of IntelinAir, which is a company which is working on drone technologies to redesign the future of agriculture and farming. Naira, thanks for being here and welcome to Robotics Today.
Thank you for hosting me today. I'm very honored to be here. So let me share my screen. Okay, so I guess I'm good to go. Thanks again for having me here. It's a great honor for me to have this opportunity to present some of our recent work that may have impact for robotics for this audience. So I will talk today about safe learning and control with L1 adaptation. And to get started, we just have these 2 animations here that show how the recent applications of reinforcement learning methods have created great impact across not just our community, but widely across the globe, like the animation on the left from DeepMind. I checked today, has more than 10 million views. That basically shows how the agent learns to run, jump, climb without having any prior model. It learns from its own mistakes, collects data, fails again, collects data, learns, has a reward function which keeps it moving forward, and so on. On the right, you see the Rubik cubic that I'm sure many of us have played in our young days with it. So it can be today reconfigured with a robotic arm. So while these applications seem very impressive and they show what artificial intelligence methods or machine learning methods, like we would like to say, can achieve from having data, having learning methods, obviously we cannot afford having these methods on safety critical systems. Safety critical systems will not forgive mistakes. We cannot allow failing, collecting data, trying, learning, failing. So every crash here can be catastrophic. Human deaths are not allowed. So accidents can be very expensive. And we have experience here of flying the Learjet. We are not just talking here artificially. The airplane on the left, you will see through this presentation numerous times. The drone here is a picture taken in our lab. On the right, we have the Waymo car. My student is working in the company. So these safety critical applications can punish us severely if we afford playing with them, assuming that we can have a mistake, collect the data, learn on the go. So let's look what's happening in a typical setup when we try to collect the data and use an optimized controller like that. Typically, we have a model learning block that learns the model from the data. There is an optimization that produces a controller, and the controller drives the system. So what can happen that the external disturbances or the modeling errors can basically destabilize the system. What one needs to do, one needs to understand that the safety must be built into the control architecture from the beginning by design. So this means that we need to have an augmentation with a safety controller that would ensure the safety of the system throughout the learning process. So no matter what are the mistakes, errors, data collection, learning, the safety must always be there so that every new knowledge acquired in this process, subject to errors, failures, and so on, will not let the system be destabilized. So looking through this type of development, so what do we need from the safety controller? From the safety controller, we need typically certificates of performance and robustness, which include transient performance, steady state performance, time delay margins, and disturbance rejection, something that we learn in a junior level control class, like the alphabet of control technology. So L1 adaptive control architecture that we developed over the last 15 years has proven its worth already on a variety of big platforms. As I said, I'll show some flights of Learjet. We have commercialized it for evolution autopilots of Raymarine, for some drone technology. It went into hydraulic pumps of Caterpillar. We have tests at Statoil on drone technology of IntelinAir and many other industrial applications. It has an architecture in which estimation loop is decoupled from the control loop, so we are able to tune for performance and robustness in a very systematic way and be able to quantify its robustness and performance robustness margins and its performance bound a priori and be able to be in hold of those throughout its performance. So when we augment the L1 adaptive controller to a type of a model learning controller that I described, so what we are able to do, we are able to retain the key features of performance and robustness of L1 adaptive controllers, yet at the same time benefit from the versatility offered by these machine learning methods. So this is what we will explore through this presentation, and this is what kind of makes up most of our current research program at Illinois these days. So L1 adaptive control theory, as I said, provides some type of decoupling between estimation and control and helps us to establish the type of performance bounds that we show here. So there is a desired system trajectory that one would like to follow. There is a reference system, which is a hypothetical reference system. It's non-implementable, but it describes the best type of performance that one would achieve with L1 adaptive controller if the system uncertainties were known. So it's non-implementable. So between this system and the actual system, the performance can be quantified inverse proportional to the square root of the adaptation rate, while the performance of this reference system with respect to the desired system can be quantified proportional to the filter bandwidth and augmented with an error that would be exponentially decaying dependent upon initialization error. So with this decoupling, we are able to tune the performance and robustness of the system in a systematic way. It is this architectural versatility of L1 adaptive controller that helped us to achieve quick tuning across different applications in different industries and to achieve transition to different industrial platforms. Here is a timeline how our development went. The first papers appeared back in 2006 American Control Conference, and in the same year in AIAA Guidance Navigation Control Conference, we had the first flight tests with Naval Postgraduate School on their Rascal UAVs with Piccolo autopilot. So we were doing augmentation of their outer loop to fly aggressive path-following trajectories. Later in 2007, we got NASA grants to fly their Airstar subscale commercial jet. We were able to successfully put the airplane into stall and post-stall to give the pilot smooth recovery opportunities from stall conditions. That led to joint publication opportunities with Boeing, Raytheon, co-authors, giving lots of visibility and opportunities to write papers with other companies. So here is where we got collaborations with Statoil, Raymarine, Caterpillar, Eurocopter, MBDA, Seagate. So all these companies got attracted to the technology, and there were lots of transition opportunities. Then we got the opportunity also to test on real airplanes. So while NASA was testing it on 5.5% subscale commercial airplane, so Learjet, F-16 were already the real airplanes, as you see, with pilots inside, that we were able to fly in 2015, 16, and 18. And now, with the explosion of this machine learning method, the robotics industry, we were able also to take this framework of safe learning and control and to move into robotics applications. So before I will go and show what we do with safe learning and control for robotics, I want to show some of these flight tests of Learjet, because these are very interesting and will keep everybody entertained somehow. So with Learjet, so when we go to fly the Learjet, so we have basically pilots and flight test engineers. The Learjet is a CalSpan vehicle that's variable stability system configuration, where they can basically inject some accidental configurations that they design with us carefully to validate these robustness margins that we claim theoretically. And they are able, basically with their safety switches, to take over in case if our theoretical claims don't get verified, they can save the aircraft with their safety switches. That's why they take the risk to fly into these configurations. So they're going to test in the next movie that I'm going to show, they are going to test for handling qualities, flying qualities. Basically, when you fly the airplane in normal configuration, you have no fasten seatbelt sign, that's flying qualities level 1. When you have some turbulence and you have fasten seatbelt sign, that's already degradation, it's flying qualities level 2, and so on. So the pilots are put into configuration when it's very shaky, and they have the Cooper-Harper rating scale in their hands, where they have to read and assess whether it's flying qualities level 1, 2, 4, from which configuration, how much they recover. And because the situation is very shaky, they are not able to read from the piece of paper. They're asking the L1 to come on so that the airplane can be stabilized, so that they can read basically in which configuration they are, how much they recover. So, I mean, just listen. So I gave a little bit preview so that when you listen, you manage to catch up, because it goes pretty fast. It's shaky, it's accidental, so it goes a bit fast. That's why I gave the preview.
Constantly overshooting my desired bank, though. Jason's probably hating life right now.
Yep.
You're right around 27. I'd recommend you just do the task with L1 on and don't do both tracks.
Got it. All right, so you did not get adequate on that one?
Okay.
Okay, so if you want to run through a CHR real quick, you did not get adequate. So we're starting in...
Can I get L1 on as we do the scoring, please?
Yep.
There's your answer. There's your answer, right?
All right, L1's coming on in 3, 2, 1. Now L1 is on.
Thank you.
Rush, if you didn't ask, I was gonna.
And now it's a landing scenario, basically. Landing is very challenging. For example, NASA never decided to land with L1, but with Learjet, they agreed to land with, again, some type of abnormal condition.
200 feet.
Copy.
$100 feet. 50 feet, shallow. Looking good. There's a ground effect. You see that?
Yep.
It's uneventful to me.
Very uneventful.
So basically, this was 2015 deployment, upon which in 2016 we got in 2016 we got the F-16, which we cannot unfortunately show and talk because that's F-16. In 2018 we got the Learjet again, and here they implemented an accident from 1967, which is a lifting body incident when the aircraft goes into roll spiral mode configuration. And here in this accident of 1967, luckily the pilot survived. They have the test data from this accident, which they are able to inject into the Learjet and test it. So these tests are extremely valuable and extremely kind of precious in some sense for training the pilots, training the students. This experience is extremely invaluable for everybody involved in this process. Now just listen to the recordings.
I can't even control the airplane. You have the airplane?
The student on the left is my student, sitting there, Javier.
Hey, task in 3, 2, 1, now.
So you can feel there in high frequency, I made some high frequency inputs, excited the roll. Lower frequency, the roll, overshoot, or oscillation tendency is less.
Sounds good.
There's still some there. Pitch, I'm having no issues. Fine tracking and gross tracking are very good in pitch.
All right, and I have maneuver complete.
Now they go into engine out test.
All right, recording on in ready, hack.
Running. Okay, power's coming back.
My hands are free.
3, 2, 1, now.
Controls fixed.
And recover, please.
Okay, and recovering.
Power's back.
I'm ready to try this now with with a pilot correcting for it. So.
Okay, and I'll give it about 1 second of reaction time. I am on conditions.
All right, and then recording on my call. Ready, hack.
On. Okay, power, it'll be left throttle.
Okay.
In 3, 2, 1, now.
1 potato and recovering.
And recording off.
Okay, recording off, matching throttles.
And with L1, they come to 3-degree degradation only.
I'm ready for the recording on ready, hack.
On. Okay, left throttle coming back in 3, 2, 1, now.
I'm not touching the controls.
Nice demonstration.
Yeah, check that out. About 3 degrees of left bank.
Speeding in the rudder to match. I can feel that. It is descending a little bit, but it's...
Yeah, descending a bit, but that would be easy to compensate for.
Yeah. Okay. I think you got some good data there.
All right, recording off.
Matching power, recording's coming off.
So this is what I tell the students, that in real world, there is no zero, right? 3 degrees, pretty good. After what we saw with 20 degree without pilot, with pilot it was 12 degree. With L1 without any pilot, it was 3 degrees. So 0 is just artificial number, right? It's making all the math work. So 3 degree in real world is a pretty good achievement. And we got some press, obviously, from it. So having these demonstrations, naturally, the next thing was coming already historically into our life, were the robotics application. So the first robotics application we got, it was interesting, with this elderly care grant from NSF that got us also some press into New York Times. It's interesting that this was kind of the first opportunity that brought us, and it nicely rings a bell with a funny cartoon that would now come and entertain everybody. So deploying these drones at home environment was interesting because we could kind of bring in VR technology and study people's perception of it and kind of compare it to Cinderella, that was maybe filmed a few decades ago, and ask questions how safe she feels in the presence of birds showering her or helping her with household tasks like setting up her bed or something, because this brings up lots of interdisciplinary research, how people feel safe in the presence of these robots, because now we talk about package delivery tasks. So all these interdisciplinary research problems make our life very interesting, very rich, and the questions that we can ask and train our students become very important and far-reaching with their applications. So as I said, for this seminar series, I wanted just to pack a number of problems where we look how to do safe learning and control simultaneously. So the first problem that I want to show here is what we did in collaboration with Evangelos Theodorou from Georgia Tech. We integrated L1 adaptive controller with his model predictive path integral controller that provides a framework for solving nonlinear model predictive controls with complex constraints in near real time. So we integrated an architecture here and used it in his Alpha Pilot project environment. Here is the environment that I want to show. The paper is accepted in this year's IROS conference. Let me run the movie here and explain what's happening here. So what you see here in red is when they run the Alpha Pilot just with MPPI, basically it takes them this long time-wise to finish the lab. When they add the L1 on the top of it, they finish the lab in a much faster time. And the green segment just show that in these cases, the MPPI didn't survive without L1. And with L1, they were able to take these few other cases as well. So here is that drone racing environment. And now as we are talking actually, and Georgia Tech has reopened their campus on June 18, the students are working to fly this L1 MPPI architecture on a real drone in their Vicon environment. Just the campus opening was happening slow. We didn't get the real drone footage from their lab. Otherwise, most likely we would have had today the real drone footage and not just the Google environment. But we are very excited by this work with Evangelos, and hopefully we will have the real drones flying very soon. If not for this pandemic, we would have had it for sure. Similarly, we have integrated also again with Evangelos this L1 with differential dynamic programming and model learning. So basically, the model learner continuously improves the knowledge of the model. Based on that, the trajectory optimization does a better optimization. And in that process, as the model learning and the trajectory optimization improve, L1 ensures this safe control and safe guaranteed performance without losing the robustness and so on. So we demonstrated this in a simulation environment of this inverted card pole, as you see, so prior to learning and after learning. So when L1 is on, you see better performance in both cases. Here is the cost function plot on the right, where you see that with the help of learning, actually, by the end of the process, you achieve the same value for the cost function. But what the learning, what L1 does in the process of the learning, L1 helps you to have better robustness and better performance, while without L1, you have basically much higher value here of the cost function. So it's the contribution of L1 for the transient here is crystal clear that during the transient, it does its job by ensuring this safe, guaranteed performance. So moving forward, we want to show, so for example, if Gaussian processes could be safely integrated with L1 architecture, right? Why do we do that? For example, if the data is being accumulated, can we simultaneously use this accumulated data to learn the model without any persistently exciting signals. And Gaussian processes say the Bayesian learner can learn the model with a few data points, right? If we store them in the kernel matrix, can we learn it? And can we use this learned model, for example, for better planning purposes without any prior knowledge? Again, this paper was published and presented recently in L4DC conference that we lost our opportunity to travel. We simulated it for a quadrotor model. So what we show here is a demonstration, basically, that in the beginning, when we don't have enough data, we see the L1 contribution. The minute enough data has been accumulated, the learner takes over, and there is no need for L1. So the L1 element in the control signal dies out, and the learner takes over and acts as the main controller. By doing so, basically, you can save some of your robustness margins already for other purposes inside the system. While the robustness margins are defined through the L1 architecture, they do not change, but when they are not used already for your uncertainty compensation because you have learned the system, you can use it for other purposes. So inside your system, you can use it for better planning, better for just other purposes that your mission may require. So, for example, in the middle, you can have change of mass, center of gravity, and other things like for package delivery and so on, like a disturbance. What it implies, L1 will kick on again to pick up the uncertainty and to compensate for it till the learner again picks up enough data to learn and compensate for it. Once the learner picks up enough data to learn, L1 contribution will die out. This is a benefit of the architecture. So how to synthesize an architecture that would work in a way when you don't have enough data, L1 works. The minute you have enough data, the learner takes over and the L1 goes into passive mode. So this is the benefit of that architecture that's detailed in that paper of L4DC that can be downloaded and studied. Next, I want to talk a little bit about navigating robots in confined spaces in between different obstacles, how to build safety tubes around those. And this is relevant to our work with Marco. I mean, we have a project, again, from NRI with Marco. So we use here contraction theory. So imagine we have a nonlinear system where with modeling uncertainties. And again, we have safety critical applications, and we want to have a planar agnostic approach to certify safe tubes around desired trajectories that we want the robot to remain inside these safe tubes and navigate inside these safe tubes in between obstacles. This paper has been submitted to CDC. It can be downloaded from archive. So we designed a contraction-based controller that would keep the robot inside these safe tubes and augmented with an L1 adaptive controller that would give us multiple knobs for tuning between safety, performance, and robustness, right? So here are the multiple obstacles, and say we want the robot to follow this orange path that would be safe in between these obstacles. But the blue would run into, for example, into an obstacle, right? If we design a tube like this orange, and it's not sufficiently conservative, it would run into these obstacles. Obviously, we would like it to be tighter around the desired path so that it doesn't run into these obstacles. So what contraction theory does, it looks into this Riemannian energy as a control Lyapunov function and tries to minimize gamma, which is the geodesic path between the desired path and the actual path, by using Lyapunov function as the energy of the shortest path on the manifold, right? And we augmented with an L1 adaptive controller. And due to the architecture of this L1 adaptive controller that has this natural inherent decoupling between performance robustness, so we have these three tubes now that are inserted one into another. So the first tube would be just purely due to the initialization error. It's like a funnel. It will be this exponentially decaying performance due to the initialization error. The second tube, which is the green tube, it will be tunable based on the filter bandwidth. And the last tube, the orange tube, would be tunable based on the adaptation rate. So here is a toy example where we can simulate and show these effects. So basically, having the 3 tubes inserted one into another, if we increase the adaptation rate, so the orange and green tubes will collapse, and when we increase the bandwidth, we'll make the tubes narrow, and we'll just get closer to the desired path. So here is just the contraction controller here that you see with the blue line that may collide with the obstacle, but when we put the L1 and we tune it tighter, we can get closer to the desired path by appropriate tuning. And what this framework allows us, as I showed, that we can incorporate Gaussian processes with Bayesian learner, we can use this previous architecture together with the contraction controller to learn the uncertainties for better planning. By doing so, we can make the tubes tighter around the desired path and have one more knob for tuning. Here is a racetrack simulated, and this paper will most likely go to the Coral conference within this next month. So if we have a beginner driver, we would like to give him a wider track. For an intermediate driver, we will make the desired path with an intermediate width of a tube. For an advanced driver, the tube can be very super narrow, right? So the rediscovery metric and the retuning of L1 parameters will not be required. So under some mild assumptions, of course. So the model uncertainty, as we learn, it will be updated, but the controllers will not be retuned. So once this paper is submitted to Coral, everything will be downloadable, including the software and everything from our GitHub sites. Now I want to move to some of these big projects that exist in our group, where this type of controllers have been motivated and they can be used most likely over the next few years. So this is the project that we're with Marco. This is an NRI project from NSF on the last mile delivery. So the underlying concept is that for the last mile delivery optimization, one can take advantage of the ride-sharing vehicles and drop the packages and pick up from these ride-sharing vehicles for the last mile delivery optimization. And that's the part of the city where already you have more stop signs, that's low speed limit, and you optimize just over the random network of vehicles. Obviously, the cars have to be retrofitted with appropriate magnetic dock. The technology has to be there. Now with pandemic, we see more and more use of these UAVs for this purpose. There are some already preliminary results, both in our group and in Marco's group, that we cite here. So what we show here is an animation from our group. Paper was submitted to Wolfer. So this is an animation showing like a point of no return when a drone is trying to approach a vehicle for dropping the parcel. And there is a point from which, like a point of no return, we call it. Here we're trying to look now how to embed a deep learning type of architecture that would have computational optimization for energy savings to maximize the flight time. We call it safe learning here. Another project in our group where we're trying again to use safe learning with control is related to this virtual Sally project. All of you remember, I believe, the landing of American Airlines in Hudson River. And we know that it was the captain's decision to land in Hudson River. So what the captain did, with his 40 years of experience, he debated his options between landing in LaGuardia and Teterboro or Hudson, and he took the correct decision to land in Hudson. So it's his experience with all the neurons trained in his brain to land in Hudson, and that was the correct decision. So can our learning and optimization algorithms today reproduce similar block in our autonomous system that will take the right decisions every time to endow our autonomous systems with similar safe path planning, safe mission replanning objectives, so that at every moment a safe mission replanning can happen to ensure safety and safe mission replanning and save the vehicles from crashes and path replanning and execute everything naturally. So we call this multi-level adaptation. And this is another NSF project kind of again in our lab. Another project that we have again, we're very excited going on with Evangelos. This has to do also with resource-aware, uncertainty resource-aware control architecture, where we refer to computation as our budget, and we would like to understand how should we budget the computation for control, for perception, for navigation. So this is very interesting, and we have another collaborator from Georgia Tech here as well, Kira, so that Evangelos works with, so this work is also partially supported by NASA Langley. And we have here kind of a fast computational algorithm for collision checks that was published last year in Robotics Science and Systems Conference. All of these add to our portfolio of methods for safe learning and control. Finally, I want to give a brief overview of the cooperative path generation and path following framework that we have developed in our lab for long years. This work was funded also by Air Force and NASA, where through decoupling of path generation and path following, we have enabled multi-vehicle missions, and we have implemented it in NASA in a very challenging environment in NASA's Langley's Autonomy Incubator. Let's go through this, how 2 drones can fly. They have network dropouts here, and they have the model of the maze, but they still do silhouette-informed trajectory shaping as these 2 drones go through this maze, and they coordinate with each other to achieve simultaneous landing. So this is a time-critical mission where they coordinate with each other their arrival time. They exchange their relative error positions, and they coordinate on their arrival time. So as a kind of next step, we plan to bring this contraction, control contraction metric augmentation approaches to this to enable multi-vehicle missions in this type of constrained environments, to enable more agile collaborative missions. And with that, I guess I would like to acknowledge my current collaborators with very successful, interesting meetings all the time. My past PhD students and postdocs, all my collaborators, my current group, all the people at Air Force who enabled all these flight tests on the Aerojet F-16, and my student Arun Lakshmanan who compiled this presentation for me. Thank you all very much. I'm happy to stop my slide share and go back to this mode. Happy to take any questions if you have. I don't know how I did with timing. You can tell me.
Oh, it's great. Yeah, thank you very much for your very interesting talk. I really loved how you gave a nice historical perspective on N1 adaptive control, and to see how such a control theoretical technique has been used very successfully in the context of safe learning and control. So that was really interesting and insightful. So today we are going to have, we're fortunate to have 2 great guest panelists, Claire Tomlin from Berkeley and John Howe from MIT. So as usual in robotics today, I will ask them to kick off the panel with some questions, and then we'll take it from there. So maybe Claire, you could start.
Yeah, I'd be happy to. Thank you, Marco. And thank you, Naira, for a wonderful talk. As Marco said, really talking about the historical perspective of L1 adaptive control and the research that you've done in your group, and a beautiful set of theory and experiments. and then bringing that together with these very popular and new methods of learning, and then really bringing the two together nicely. So I thought I had 3 questions, and I thought I'd start with the more detailed one, and then maybe go to the more broader questions. And the first question is something I know you've thought about a lot, which is, as control theorists, we're very careful about models and about developing these, and you have shown this in your work, developing and in your work decoupling these bounds on performance and robustness, and the deltas that you get and the certificates that you get out of L1 adaptive control. And then you bring in learning. And learning, and you showed, very sort of elegant frameworks, and with your MPPI work and your DDP work, how you can really marry these together. But what, maybe you can talk about this kind of piece at that intersection where, very simply put, you have a model, you've developed your L1 adaptive control framework, and then you're applying that in a system where, all of a sudden you're faced with an unknown environment where the uncertainties and the things that are coming at you from the environment just violate those restrictions. That's the kind of dichotomy that I think we're faced with, and you've been able to maneuver that beautifully. And I'd like you to just comment on that and talk about, how you do that. Like, perception, learning and perception. How do we deal with these big uncertainties that come and violate what we've already developed as control theorists?
How much time I have to answer that question? It took us 6 months with Evangelos day and night to make it work. So that MPPI L1 that you saw in that Google slide, it was 6 months work. It was how to put an architecture that would make it work, because first is the architecture, right? So it took us really 6 months to make that L1 MPPI and the L1 with GP that was in L4DC to work, because first, and I have to give here Evangelos lots of credit, because he pushed me to do it. He said, why don't you do it? Because it's very important for the community. If you don't do it, others will do it and they may not do it right. You better do it and you will do it right. I said, okay, well, let me do it. So the first question is that, can GPs be integrated with L1, just feasibility question? And at first we looked at that. Can GPs be integrated with L1 as a feasibility question? Not that to achieve something more, but can we have a GP inside L1 that can learn, and this whole learning will be safe? So, and there are a few ways you can put this GP inside L1, like it's an architecture, right? So how to put it right so that it can learn, and when it learns, for example, L1 can go into passive mode because it's learned already. You don't need it to do anything. If I know, because L1 is needed for adaptation, for robustness, and if I know, then I don't need it, right? So how to have this correct architecture? So you see, what I always like to say and emphasize, that the most important thing are the architectures, right? You can say you can put one fixed gain control architecture and struggle all your life how to compute your control gain, how to solve your optimization problem to compute your control gain so that it does the job. And then all your life you are solving your optimization problem in a better and better way. Another parallel philosophy is how to synthesize the correct architecture so that it does the job better. So in this process, we were struggling how to make the correct architecture, and the correct architecture, according to me, is the one so that when the learner learns, L1 dies, right? And it dies correctly. It dies as much as I have learned, right? So how to come up with this architecture? It's work. It's 6 months postdoc work, okay? Then L1 MPPI, where was our challenge, right? MPPI is super fast, right? It has its sampling requirement. L1 has its own way of being fast estimation, slow control. And how to make all these samplings work with each other and work robustly so that it works. It's 6 months work, right? And there are postdocs involved, students involved, day and night talking, meetings. So, I mean, if some of your students want to work with us, we can have them join our meetings, but it takes persistence, it takes work. I'm thankful to Evangelos for pushing me to do it. It was work. The journey was work. Now we have opened a whole new set of opportunities. We'll take it further. It's not one quick answer.
Yeah, okay, thank you. That's maybe now leading to a broader question that you've also thought about, I know, is deep learning. So, you know, as we integrate perception into autonomous control systems, we're going to be using deep learning mechanisms, right? That's what 99.9% of the computer vision community is using. What are your thoughts about that? What are your thoughts about analyzing or verifying deep learning components within control loops?
So it's going to be hard. It's not going to be trivial. But one thing I know, if we want these systems ever to be certified, the thing that I have learned, and this may change over the years, but I know that any software that gets modified on the flight will not be certified today. At least this is what I learned from Louis Shaw, who is my colleague at Illinois and who is great authority for certification community. He always says any software that gets modified on the flight, and this is these are some of the tough lessons learned also from the 737, that cheap, quick certification solutions may not work. So one has to be very careful when you talk of deep learning going into safety critical systems and not being very thoroughly and carefully analyzed. So again, the architecture has to be correct. And the architecture correct implies you need to have some type of switch that there is this expert controller that's always there, that whenever your uncertainty estimation threshold gets violated, right? You can have a deep learning there that takes raw inputs, outputs a controller in a very benign environment. But when your environment is not benign and it becomes very adverse, basically you have uncertainty type estimation that gives you thresholds that are very violated, and that has to be pretty conservative and safe for your operation. When that gets violated, that you have to kind of have an expert controller that takes over, overrides everything, shuts down the system, and navigates safely. I would say architecture. What makes your system safe? Architecture has to be right.
Yeah, thank you, Naira. And then maybe one more question before we move over to John's question. Model-free learning. What is the place in all of this for model-free learning? Is there a place?
I don't believe in
it. That's why I'm asking you.
Well, model-free learning, you can play with these cubic rubrics, so, okay, but not with safety critical systems. I mean, model-free learning, I can build a toy, give it to a 5-year-old kid to play with it, but not with safety critical systems. I'll do my own. It's a due diligence. So K-12 outreach, we can build toys and go do K-12 outreach. It's also valuable. We can engage the smarter kids into our community and then help them do system ID and model-based controllers. That would be my approach.
Thank you, Naira.
Well, with insightful yet perhaps controversial statement, we can lead the discussion to our other guest panelist, John Howe.
Great, thanks, Marco. Naira, thanks for a great talk. It's great to see the work you've been doing on the L1. I mean, you and I have spoken about it before, but it's always fun to see the videos of the things that you've been able to do recently. I had an open-ended question that was similar, I think, to what Claire was just asking in terms of, you know, as we begin to get close to deploying these types of systems in the real world, you know, you start getting these sort of unexpected sort of consequences in the sense that you mentioned sort of maybe in a sandbox or these algorithms start learning and going outside the box of things that you maybe had thought about before. So from a performance perspective, that's good, but from a sort of certification perspective, maybe not so good. and that type of uncertainty and how it's going to behave translates into conservatism. And then you start seeing people talking about, well, maybe we shouldn't put that on there. Now we've faced this as a community all along, thinking about adaptive control, but I'm just thinking in terms of, for the student audience out there, is there perhaps advice you could give on types of research directions and things that they could be thinking about to address this problem where, maybe for the past decade, we've thought about how to make things better. For the next decade, maybe the focus is on not just better, but actually saying a lot more about how it's actually going to behave. Can you actually give a type of certification and things like that? So just thinking in terms of advice for researchers, what types of things should they be thinking about as they move forward in their careers?
Yes, that's a very good question, John. And what I think we should do, maybe you, me, Claire, and other senior people here, together with the junior people, we should maybe form a type of consortium and invite FAA to talk with us how the modern paradigms for certification need to be formed that would not depart the conventional paradigm, but would leverage the existing practices, yet allow room for modern methods to make their way there, along with practical evidence and simulations and all these experiments. Because as you see, I'm trying to build up the way we have worked to build up. So if there are people who want to come and start a conversation, I'm ready for that. But we need to have a consortium of people who are ready to get together, to support each other, to negotiate. That requires a big room with lots of people. Even it can be a Zoom room. Obviously, in a physical room would be easier, but it requires certification is not one-person game. It's lots of people in one room. That's industry, that's government, that's FAA, NASA, Boeing, I don't know, MIT, Berkeley, Stanford, I don't know. So it's lots of people in one room. That certification can be done only that way.
Yep. Thanks. One last question. It won't be quick because it's open-ended as well, but as you look at these ICRA and IRAS conferences and you see just how many papers have the words deep learning in them, which I think is bordering on more than half, one of the concerns that came up in one of these debates about the future of these types of conferences was that we'd be starting to generate a lot of sort of researchers whose answer to every problem is deep learning, and that we start losing an ability to solve some of these problems using other techniques. And any advice on sort of moving forward? I mean, it's as a field, I mean, where it's like if you have deep learning in the paper title, you increase the probability of it getting in. On the other hand, it's not always the solution. And so it's a question of how do we retain the skills as a robotic community, and yet still recognize the value of this technology, but also its limitations.
Well, there is always rigor. There is always ad hoc. There's always a proportion, right? I always say there's always 30% of good work, 30% of mediocre, and the rest should not exist. So it's the same, I guess, split. I guess we just have to be critical and constructive with respect to each other's work and try to be supportive in our critical comments, to be constructive and helpful for juniors, to be good role models.
Yep.
And some people just use the deep learning to be in fashion and to get attention and to be published. I mean, human factors always play a role. People become friends sometimes just to get votes. So, I mean, just a little bit more careful and rigorous approach to reviewing peer review work. Everything matters.
Okay, great. Thanks, Naira. Thanks for your presentation.
My pleasure.
Thank you very much, Claire and John. We also have quite a few questions from the audience, along with several comments actually complimenting you for the talk.
Thank you.
Maybe Nima, you could start with your question. We
Yes.
have 3 students that are doing the heavy lifting of distilling the questions from the audience and asking the most representative ones. Nima, go ahead.
Yes. Yeah, so first question is from Hamid Reza. He asks, what is your main reason for using L1 adaptive control over other robust control methods?
Okay, that's a very good question. That's true that L1 adaptive controls input-output map is identical to internal model controllers input-output map, but L1 adaptive control does not have a model inversion block to it, so it's forward method. It does not invert, so it's very easy to implement, and it's easy to accommodate all kinds of model knowledge updates that you acquire on your way. So in that sense, its tuning nodes are very easy. Decouples its estimation from the control loop. So any new knowledge you acquire about the system, you put it into your system predictor, and it helps you to get it closer to the main system. And its robustness, you just tune with the filter bandwidth. So its tuning is just much easier. While if you use an internal model controller, every new knowledge that you acquire about the system will require you to do model inversion again and again and again and again, which makes it very complicated. For nonlinear systems and more challenging classes of systems, actually it's not even clear how to do it.
Okay, then we have a question from Nia.
Yeah, so I have a question from Blake. Would you mind elaborating on your collaboration with Raymarine? What unique constraints of marine autopilot design are well addressed by L1 adaptive control?
My collaboration with them, that was in 2012-13. What would you like me to elaborate? I mean, that was kind of a consulting arrangement. I can't talk too much about it, but that was their autopilot, evolution autopilot, and whatever is on their webpage, that's all I can say. It was, I mean, we couldn't publish it. It was unfortunately a little bit consulting arrangement. I can't talk just too much.
Okay, that's absolutely fine. We have another question from Rachel.
Yeah, hi. So Lena Benbali asks, or mentions that bringing contraction with learning and the disjointed architecture that you mentioned seems to be key for a lot of significant future developments. I was wondering if you had any comments about that, or kind of what you see bringing into future developments.
Oh, I see lots of potential there, because if we make all this work, we will have a complete framework from planning to low-level control, enabling more agile and versatile missions for autonomous systems. We look forward to making it all happen. So this is still work in progress. The first papers will go to this Coral conference, and then we'll see how it develops in future. Just follow our website, our archive postings. You'll see how it develops.
Awesome.
Okay, and actually there is a follow-up question from Nima in terms of robust trajectory generation. Nima.
Yes, thank you. So Hamid Reza follows up with, have you compared your proposed trajectory generator with other robust generator methods?
So which trajectory generation method do you mean? We have a few, and yeah, we compared. So there is, I mean, what is of interest here? So we have Bezier curves, we have this DDP here, we have MPPI, we have so many methods in different cases. And it depends upon the context, upon the application. So when we had this MPPI with L1, it's because Evangelos had it in this alpha pilot. He wanted just to put L1 on the top of it. When we had the same DTP putting L1 on it, it's again, it was his interest there. We have in our NASA project, we have the Bezier curves. We have some RRT also there involved. So in every case, we have something different. It's not like we have one trajectory generation method and that's it. We have a variety of different things in different places. And now we have this also contraction metric coming. So no, didn't do kind of, we never wrote a paper on comparing different trajectory generation methods. In some sense, we haven't done such analysis.
Great, thank you.
Okay, I do actually have many questions, but I will start with one. one of the attractive features of L1 adaptive control are the sharp theoretical guarantees. So I was wondering if you could elaborate a little bit on to what extent you were able to lift those theoretical guarantees in the context of augmented MPPI or augmented GP and so on.
Lift the guarantees or what?
Basically, provide the theoretical guarantees in those contexts that build on top of the traditional L1 adaptive control guarantees. So
in the contraction paper and in the L1 GP paper, I mean, you can download those from archive and see the proofs are done completely provided. In the L1 MPPI paper and the L1 DDP paper, these proofs are not provided yet. The L1 MPPI paper that went to IROS and the L1 DDP paper has not been yet posted anywhere. But the framework from this contraction L1 can be adapted to provide the proofs also there. We are just hopeful that it's doable. But for the contraction, the paper is on archive, and for that L1 GP, it's also on archive. So those proofs, we're hopeful that they can be adapted to those papers as well.
Okay, great. There is also a question from Jeanette.
Sorry, I have to unmute myself. So thank you for the great talk, Naira. That was really interesting. And you have answered strongly to Claire's question on model-free versus model-based, that you're strongly for model-based because you have the ability to basically introduce a lot of guarantees. But even in a model-based approach, there are lots of opportunities for learning, right? Lots of different ones. You could learn the some state representation if you wanted. You could learn the dynamics models, maybe cost functions. Where do you see are the most interesting opportunities for learning, and where should you keep maybe non-learning based methods in the overall system architecture?
Okay, that's a good question. So learning is not coming for free. You need to allocate computation for that, right? CPU, GPU, I mean, today it has to be like, what's the beauty of these MPPIs? Because it's parallelizable, so it can be implemented in real time. And so there is a price to be paid. Nothing comes for free. So this is very important to keep in mind. The minute we deploy these autonomous robots, like this delivery drone, the project that we're with Marco, right? It has to carry a payload. The minute you put a payload on UAV, it reduces your flight time. So you have to budget. If my UAV has to fly 15 minutes and deliver a package, right? And it has to deliver a package that's 2 pounds, for example, and it has to fly 15 minutes, right? How much learning it can do, right? So you have to budget. So it has a certain amount of CPU, GPU, whatever it has certain amount energy based on its batteries, right? So that's why we are now exploring, for example, this deep sense that's provided by one of our professors, Tarek Abdelzahar, that has energy efficient computation with his deep learning. For example, we go already to that level. Anything we can explore for energy optimization to maximize the flight time so that we can pick up more packages for longer distances. So computation is your budget, okay? So think how much learning I want to do versus what distances I want to cover, what robustness I want to have. They are all in trade-off. If 20, 30 years ago, my only trade-off was T plus S equals 1. Today, my trade-off is not limited to T plus S equals 1, okay? Today's trade-off is a lot more. It's this computation, it's learning, it's everything. So everything gets into one big equation that none of us have yet maybe figured it out. But the trade-offs are very complex in today's learning plus control environment. So the control trade-offs were performance plus robustness. In learning plus control environment, the trade-offs have not been yet completely figured out. And those have to be figured out before we can answer the questions that you are raising. And these are actually very good questions, and they can lead to lots of interesting PhD dissertations.
Thank you.
Next, Luca.
Naira, thank you so much for the talk. It was very interesting and was an incredible perspective, I think. So I had a question which I believe is a follow-up on what John was hinting to, and Claire as well, which is in general certification for robotics and autonomous system, as well as the role of perception. And so I was seeing, like, in the videos that you had at the beginning, this Learjet system in which you inject failures and disturbances, and essentially you evaluate the system and the response of the system with and without L1. Certify the performance, or validate the performance. And my question for you is, do you envision a similar technique to be useful for, I don't know, certification of self-driving cars, certification of robots, this kind of disturbance injection? And I guess the broader question here is, what is the main takeaway on your side out of the deployment of these very complex and real-world systems? What do you want to share with the young researchers?
Young researchers, I would suggest get your hands dirty with real-world systems. Give yourself the opportunity to experience the real-world systems, right? The real-world systems will give you the type of experience that the simulation environments don't give. So the learning experience that you get from touching the car, touching the drone, going, taking the data, collecting, coming, trying, going back and coming, shapes you as a different thinker. That thinking that gets into your brain after that experience, it's invaluable. You can't get it otherwise. You just can't get it by proving theorems, publishing, going to conferences, presenting. That's a different experience. You want to publish papers, to go to conferences, to present, get peer reviews, comments, criticism, but getting under the car, loading your software, coming back, testing, going back again, and doing that for months and years, it gives you different muscle. That's a different experience. You want to have it, and it creates a different thinker, and that's very important. I highly recommend all of you, don't lose your young years by just being analytics. Get that practical experience, because today's reality is the reality of autonomous systems, and it's very important to understand it from end to end. What does it take? What is the epsilon? What is the delta? Go and try to understand that 5 is greater than 4. It's not like 5 is greater than 4, we all know, but it's different when you sense it with your, this is what it means, this is what it means. And you get it when you go there. It's important. Don't miss your chance.
And any thoughts about self-driving cars, certification process, anything else that you want to share about that?
Well, self-driving cars and airplanes are different in some sense. While they all have control systems and they all have certification challenges, the challenges of airplanes are different from the cars, because for airplanes it's the stability, it's the stability mostly, right? For cars, it's more the navigation in confined spaces, it's the perception, it's a close contact with obstacles that the airplanes don't have. So these are different, and therefore the certification challenges are also different. For the cars, how you would integrate the perception, the close contact with pedestrians and different obstacles around. So even the communities of certification will be different. But I mean, one can understand what's common and what's different, and leverage what's common, share the lessons learned, understand the differences, and try to work on the differences with different communities, on the common things with the common communities. I think that's very important, that be partners with the right industries who are pushing it the right way, right? Because in self-driving cars, I guess the level of autonomy that people are trying to reach is the level 5, but today at the best, we have level 3, right, around. I haven't heard of level 4 still being in the streets somewhere. So the partnership today is the most important thing, that you need to have industry partner and government partner when you want to go through certification. And if you don't have all three in one room, industry, government, academia, certification may be just too far and unachievable.
Great comment. Okay, thank you.
Thank you, Luca. Rachel has another question from the audience.
Yeah, I do want to say I love the advice of like, get your hands dirty. I think it's fantastic. We have a couple of anonymous questions that ask, what are the open problems or limitations to L1? What's an example where an L1 scheme might fail, for example?
Well, yeah, there are. I mean, the open questions of L1 are the same like open questions of control theory, right? If you talk of no minimum phase systems, output feedback, and so on, these questions also exist for L1. We did not solve those problems. We just have an architecture that within the existing limitations, within the existing assumptions, gives us an implementable architecture with easily tunable nodes for which we can quantify the performance and robustness in a systematic way. We can predict the margins and the performance, and we can tune for those, right? So the open questions exist. If you say output feedback for non-minimum phase systems, we have very limited cases where we have solutions for those. So, I mean, these questions exist. So if people want to work on this problem and they want to reach out to me, I'm happy to point them to the very last paper and the last dissertation of our group where we couldn't make further progress, and they can start from there.
Thank you. And we have another question from the audience. Niha?
This question's from Wasim Haddad. Have you looked into extending L1 adaptive control to a hybrid setting to address hierarchical architectures?
No, I have not.
Okay, so I have one more general questions related to also what the points that John was making and so on. For our students, what resources you would suggest in order to get a better appreciation of control theoretical tools that need to be accounted for, even if they are now using more, computer science tools such as AI? So what resource or what techniques you would suggest that everyone should absolutely know?
I think before learning AI, they have to fundamentally learn estimation. They have to learn backpropagation. They have to learn the foundation. The mathematical foundation is very important. Never use or apply anything blindly. I mean, there are so many tools today in AI that, like this ResNet, this and that, you can download, apply, use, but don't do it without understanding. Try at least to understand some of the basics. What are you applying? How are you applying? Get a simpler version of that. Try to understand what's happening. And then maybe once you are familiar with the tool, then you can maybe get an advanced tool that try to apply, see what you get. But the mathematical foundation is very important, very important. Actually, what you see in my background, in my alma mater, I always say the epsilon delta proofs I learned in this university. So it's Yerevan State University in Armenia. So that epsilon delta proofs, the math, the underlying foundation is very important. You can't engineer safety critical systems without the right level of rigor. So be rigorous. Otherwise, the safety critical systems will punish you in a bad way.
I totally agree. And Luca, you also have a question?
Yeah, the question about something that you mentioned, Naira, at some point, you mentioned virtual reality and understanding or factoring in human perception of risk, the perception of risk from the user. I was just curious about how do you factor in that kind of perceived safety into the mathematical model?
Yeah, that's a good question. What we did, we worked with a psychology collaborator at Illinois, Francis Wang. So psychologists know apparently how to measure humans' perceived safety. If the humans, they measure this fuzzy driver, these are called GSR signals, so that the skin conductance, heart rate, and head tilt, if they measure, from that skin conductance signal, they decompose, they get this fuzzy driver, which measures humans' anxiety level. If it has a certain level of activation, so they build a machine learning model, and they can judge whether the human is scared, excited. So the anxiety level they can measure. But their machine learning level appeared to be very primitive. It was giving lots of false positives. Basically, we had to become more sophisticated. For example, build a machine learning model with a latent variable using human attention state to eliminate lots of their false positives, to get a more reasonable human anxiety model for path planning that we started using in a cost function to do path planning for a drone, for this package delivery task or flying around humans, so that the human won't feel stressed when the drone flies around. So that's maybe a subject of a separate talk, but we have a paper from last year ICRA workshop that you can download maybe and check. Actually, it was published even in ACM Transactions, some invited this issue on human-robot interaction could be downloadable already from.
I'll check it out. Thank you.
Jeanette?
Yeah. We're now at the end of today's seminar. And I would like to thank Professor Naira Hovakimyan again for a very interesting talk and the great Q&A. And your message to the students about getting your hands dirty with real robots was actually also brought up last week, or 2 weeks ago, actually, by Scott Kundusma from Boston Dynamics. And there seems to be a theme here. I would also like to thank our guest panelists, Professor Claire Tomlin and Professor Jonathan Howe, for their great questions. And thank you to the audience for coming and submitting all the questions. I hope you're all coming back on July 24th, when Sid Srinivasa from the University of Washington will give a talk on his research. So thank you, everyone. Goodbye, and have a really nice day.